let's talk about derivatives of both exponential and logarithmic functions. I'm going to start by considering exponential functions. What is the derivative of the function f of x equals a to the x, where a is a constant? We can apply our limit definition of the derivative. That's going to give us limit as h goes to 0 of f of x plus h minus f of x all over h. Or limit as h goes to 0 of a to the x plus h minus a to the x all over h. Now this first term, this a to the x plus h, can be written as a to the x times a to the h. That's just my product rule for multiplying exponents. When we multiply two expressions with exponents, we add the exponents. And by doing this, I now have a common factor of a to the x in the numerator. So I can pull the a to the x out of the numerator, and I'm left with a to the h minus 1, and we still have all over h. And so we're taking the limit of this expression as h goes to 0. That common factor, that a to the x, doesn't have any h's in it. So when I take the limit as h goes to 0 of a to the x, I just get a to the x. So we've got this a to the x times limit as h goes to 0 of a to the h minus 1 all over h. That a to the x, that first piece in this product, is actually the original function. So what this is telling me is that my derivative, f prime of x, is equal to my original function times this limit, h goes to 0, a to the h minus 1 over h. And this limit, notice it doesn't have any x's in it, so that limit is going to be a constant. So this is telling me when we have exponential functions, our derivative is actually proportional to the function itself. The slope is proportional to the y value of that function. So my derivative is going to be my function times some constant. And the value of that constant, the value of that limit, depends on what a is, depends on the base of the exponential function. We are going to define our natural number e to be the base that makes this limit equal to 1. So the limit as h goes to 0 of e to the h minus 1 over h is equal to 1. And that number, that natural number e, is approximately 2.7. It's actually an irrational number. The decimal continues forever. So that means when our base is our natural number e, the derivative of e to the x equals 1 times e to the x, or just e to the x. So the derivative of the function e to the x is e to the x. I have graphed on the screen. This is in red. I'm highlighting it right now. This is the graph of my exponential function e to the x. And what this derivative is saying is that anywhere on this graph, the y value and the slope are the same. So for example, if I'm at the point 0, 1, so when x is 0, y is 1, that point has a tangent line with a slope of 1. And as the y values are increasing, the slopes are also increasing. The slopes are always equal to the y value on that graph. All right, let's now use what we've learned to see if we can find the derivative of our natural logarithm, which is log base e. And then finally, we'll summarize these derivatives in general. So f of x equal ln x, f of x equal the natural log of x. That function is the inverse of our function e to the x. So I've got the equation y equals ln x. That's the function I want to find the derivative of. This is equivalent to saying e to the y equals x. The inverse of y equals e to the x, I would just switch the x's and y's. I get e to the y equals x. I can use my implicit differentiation to find the derivative of e to the y equals x, which is the same as my natural log function. All right, so the derivative of e to the y Well, we just learned the derivative of e to the x is e to the x. So using my chain rule, the derivative of e to the y should be e to the y times dy dx. Derivative of the outside times the inside. And then the derivative of x is just 1. So solving for dy dx, I get dy dx is 1 over e to the y. This matches with what we've learned about derivatives of inverse functions. The derivative of inverse functions is reciprocals. So derivative of e to the x is e to the x, so the derivative of the inverse of e to the x would be 1 over e to the y. And e to the y is the same as x, so the derivative of my natural log function is 1 over x. All right, so let me just summarize this really quickly. So we have learned that the derivative of e to the x is e to the x. If we change that base, so if we have a different base, a to the x, where a is any constant, it turns out we're going to get natural log of a times a to the x. So the derivative of a to the x is natural log of a times a to the x. We've also learned that the derivative of natural log of x is 1 over x. If we have a logarithm with a different base, so log base b of x, the idea is you can use that change of base formula, which would say that log base b of x is equal to log base e of x divided by log base e of b. And then the derivative is going to be 1 over ln b times x. That's because this divide by ln b in my change of base formula is actually a constant. So we've got 1 over ln b, that's a constant, times ln x. When we take the derivative, that constant's going to stay there. We're going to get 1 over ln b times 1 over x. And that's going to give us our 1 over ln b times x. So these are some new derivative rules, derivatives for logs and exponentials. And we can use these new derivative rules in combination with everything that we've already learned about derivatives. We can use these rules with our product rule, quotient rule, and chain rule. So let's do an example. Let's find the derivative of f of x equals natural log of sine of x. This is a chain rule problem. This is not multiplication. This is a chain rule problem because the sine of x is inside my log. This is a composition of functions. And so we just learned that the derivative of natural log of x is 1 over x. So if I want to use my chain rule on this, my outside function is my natural log. Instead of natural log of x, I have natural log of sine of x. So this outside derivative is going to become 1 over sine of x, kind of like my 1 over x. But I'm using the chain rule, so I'm going to have to multiply by the derivative of the inside. My inside function is sine of x. That has a derivative of cosine x. 1 over sine x times cosine x is cosine x over sine x. We could also write that as cotangent x. Now, I do want to show you, if it's easier, especially with these logs and exponentials, you can write this out using the u's. We did that when we first introduced the chain rule in this class. So we could say our inside function, our u, is sine x. So then f of u would be ln u. The derivative of sine x is cosine x, and the derivative of ln u is 1 over u. So using the chain rule, I have to multiply these derivatives together, and I get cosine x times 1 over u. That 1 over u turns into 1 over sine x, and I'm going to get that exact same answer, cosine x over sine x, or cotangent x. Here's another example. Find the derivative of f of x equals e to the 3x squared. This is another chain rule problem. It's not multiplication, it's not the product rule. That 3x squared is inside my exponent. So this is a composition of functions. We learned earlier in this video that the derivative of e to the x is e to the x. So my outside function is e to a power. When we have e to a power, we get e to the power. So the derivative of e to the 3x squared is going to have an e to the 3x squared. That's my outside derivative. The inside function is the 3x squared. That's inside the exponent. Derivative of 3x squared is 6x, and the chain rule says I multiply these things together. So I would just write that derivative as 6x times e to the 3x squared. We can also write this out using that notation with the u's if that makes things easier. In this case, I would say u is 3x squared. So my function is e to the u. Derivative of 3x squared is 6x. Derivative of e to the u is e to the u. Chain rule says we multiply these derivatives together, and I get 6x times e to the u. Finally, replacing that u with 3x squared gives me my final answer, which is the same as what I got earlier. Here's another example. Find the derivative of 10 to the x times x to the 10. Now this one is a product rule because we have multiplication. I'm going to let my first quantity equal 10 to the x, so f is 10 to the x. G is x to the 10. Now let's find the derivative of each of these, and then we can use our product rule. Notice that these two expressions are going to have different derivative rules. In 10 to the x, the base is a constant, and the variable is in the exponent. This is an exponential function, so we're going to use that rule that we just learned. The derivative of a to the x is ln a times a to the x. In this case, my a is 10. So I'm going to get natural log of 10 times 10 to the x. Then for g, now the base is the variable and the exponent is a constant. That's when we use our power rule. So derivative of x to the 10 is 10 x to the 9. Putting this into my product rule, I have to take f prime times g plus g prime times f. So ln 10 times 10 to the x times x to the 10 plus 10x to the 9 times 10 to the x. We can leave our answer like that. There really isn't much we can do with that answer. If you want, I guess you could factor it. There is a common factor of 10 to the x in both terms. There's an x to the 9 in both terms. So you could write this as x to the 9, 10 to the x. And then if you factor those out, you're left with an x ln 10 plus 10. But either format is great for that answer. Last example in this video. Let me know if you have any questions.